This is your lecture 9, Artificial Intelligence Use of Causal Inference. This is your Professor T. Fareed Muhammad. This week we will delve into fascinating world of causal inference, a cornerstone methodology in data science that enables us to discern cause and effect relationships within complex datasets. By focusing on causal graphical models, we will learn how to visually and mathematically represent these relationships using directed acyclic graphs. These models are invaluable as they provide structured way to encode assumptions about causal mechanisms and to identify potential sources of bias, thereby permitting us to draw more accurate inferences from observational data. Understanding these graphical models is crucial for fields ranging from epidemiology to economics, where disentangling causal effects from mere correlations can lead to more effective interventions and policies. What is a causal inference? Causal inference is a method used in data science, machine learning, artificial intelligence to figure out whether one thing actually causes another. Unlike simple observations, which only show patterns or connections, causal inference helps us understand the real impact of actions or events. For example, scientists don't just want to know that smokers are more likely to get lung cancer, they want to prove that smoking causes lung cancer. This requires careful analysis to rule out more and other factors to confirm the direct link. In everyday life, we often assume that if two things happen together, one must cause the other. But causal inference goes deeper. It uses experiments, statistics, and models to test whether the true cause and effect relationship exists. This is important because it helps us make better decisions, whether in medicine, business, or public policy, by understanding what really works and what does not. Causal inference is crucial because it helps us make decisions based on evidence rather than guesswork. For example, when a new drug is developed, scientists don't just check if patients who took it got better. They compare it to the group that didn't take the drug to ensure the improvement was actually due to the medicine. This way, they can be confident that the drug works and is not just coinciding with recovery. In fields like healthcare, economics, and education, causal inference helps policymakers and professionals understand the real effects of their actions. For instance, if a school introduces a new teaching method, causal inference can determine whether it's truly improving students' performance or if other factors like student motivation or teacher experience are responsible. Without this, decisions might be based on incorrect assumptions, leading to wasted resources and harmful outcomes. So, just to reiterate, in the causal inference enables evidence-based decision making by isolating the impact of specific interventions, evaluating the effect of new drug on patient recovery rates, controlling for other factors like age and lifestyle is also a good example. Correlation versus causation. Correlation means two things happen together, but it does not mean one causes the other. For example, ice cream sales and drowning incidents both increase in the summer. However, eating ice cream does not cause people to drown. Both are influenced by the third factor, hot weather, which leads to more swimming, and more ice cream consumption. Mistaking correlation for causation can lead to wrong conclusions. Causation, on the other hand, means one event directly leads to another. For instance, smoking causes lung cancer because scientific studies shown direct biological link. Understanding the difference is vital. If we assume correlation means causation, we might make poor decisions like banning ice cream and reduce drownings. Causal inference helps us avoiding such mistakes by testing whether a true cause and effect relationship exists. So, just to reiterate, the correlation measures association while causation implies a direct effect of one variable on another. So, as I just mentioned, I'll not repeat that ice cream sales and drowning incidents are correlated. Both increase in summer but does not cause the other. Causal graphical models. These models are visual tools like diagrams that show how different variables influence each other. One common type is called directed acyclic graph or DAG. These graphs use arrows to represent cause and effect relationships, making it easier to see how changes in one area might affect another. For example, a DAG could show how education level impacts income, which in turn affects health outcomes. These models are useful because they simplify complex relationships instead of looking at raw data or statistics. Researchers can draw a graph to see potential causes and effects at a glance. This helps in fields like medicine, where understanding how factors like diet, exercise, and genetic interact can lead to better treatments and policies. So visual tools like DAGs, as mentioned earlier, that represent causal relationships between variables, and the DAG showing how education level, income, and health outcomes are interconnected is also an area that we can ponder upon. A directed acyclic graph or DAG is a type of diagram that shows cause and effect relationships using arrows. The directed part means arrows point from cause to effect, and acyclic means there are no loops. An effect cannot circle back to influence its own cause. For example, a DAG might show that exercise leads to weight loss, which then reduces blood pressure. This helps us see the chain of effects clearly. DAGs are powerful because they help us visualize how one change can lead to another. If we want to lower blood pressure, the DAG shows that increasing exercise might be an effective strategy. By mapping out these relationships, scientists and policymakers can focus on the most important factors and avoid wasting time on things that don't directly influence the outcome. In a DAG, nodes represent variables such as study time, exam scores, or stress levels. The edges are the arrows and cannot. We can actually revisit that. The edges are the arrows that connect these nodes, showing how one variable influences another. For example, an arrow from study time to exam scores means that studying more directly affects test performance. This simple structure helps us understand complex relationships. By looking at the nodes and edges, we can trace how changes in one area might ripple through a system. For instance, if stress levels affect study time and study time affects exam scores, then reducing stress could indirectly improve grades. DAGs make it easier to see these connections and help plan effective interventions. DAGs don't just show relationships, they also encode assumptions but how variables influence each other. For example, a DAG might assume that advertising spends directly increases sales, but sales don't affect advertising spend. These assumptions are based on real world knowledge and help guide the analysis. Encoding assumptions is important because it enforces researchers to be clear about their beliefs before analyzing data. If an assumption is wrong, the DAG can be adjusted. This process helps avoid mistakes like assuming a marketing campaign caused a sales boost when another factor like a holiday season was actually responsible. Bias is crucial. Inference. In reality, let me rephrase it. Bias in causal inference happens when an outside factor called a confounder affects both the cause and effect we are studying, and that is crucial for us to know. For example, age might influence both coffee consumption and heart disease risk. If we ignore age, we might wrongly conclude that coffee causes heart problems, even if the real issue is that older people drink more coffee and are also more prone to heart disease. DAGs help identify these confounders by showing all the variables involved. Once we spot a confounder, 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 we can adjust our analysis to account for it, leading to more accurate conclusions. This is why DAGs are so valuable. They help us see hidden biases that could otherwise mislead us. The backdoor criterion is a rule that is used in DAGs to find and adjust the confounding variables. It helps us identify paths in the graph where the confounder might be sneaking in through the back door, influencing both the cause and effect. For example, if we are studying how education affects health, socioeconomic status might be confounder because it influences both education and health. By applying the backdoor criterion, we can adjust our analysis to block these misleading paths. This might involve statistically controlling the socioeconomic status to isolate the true effect of education on health. These results are in a clearer, more accurate understanding of causality. Now let's look into more depth the colliders in DAGs in expanding our current knowledge of causal inference. A collider is a variable that is influenced by two or more other variables. In a DAG, colliders can create misleading associations, making it seem like two variables are connected when they are not. For example, hospital admission is a collider in the relationship between air pollution and asthma attacks. Both air pollution and asthma attacks can lead to hospital admissions, but that does not mean air pollution directly causes asthma attacks in every case. If we don't account for colliders properly, we might draw incorrect conclusions, such as thinking air pollution and asthma are unrelated, when they actually are. Colliders can trick researchers into seeing patterns that don't reflect true causality. So let me repeat myself again. Colliders can trick researchers into seeing patterns that don't reflect true causality. For instance, if we only look at people who were admitted to the hospital, we might miss the bigger picture of how air pollution affects asthma in general population. Whenever I repeat something, that is pretty much a profound statement. Understanding colliders help us avoid these mistakes and interpret data more accurately. A confounder is a variable that affects both the cause and effect we are studying. For example, if we are examining how exercise affects cholesterol levels, diet might be a confounder because it influences both how much someone exercises and their cholesterol. To get accurate results, we need to statistically control for diet meaning we adjust our analysis to account for its influence. Adjusting for confounders help us isolate the true effect of variables we are interested in. Without this step, our conclusions might be skewed. For instance, if we ignore diet, we might think exercise has a bigger or smaller impact on cholesterol than it actually does. By controlling for confounders, we ensure our findings are reliable and reflect real cause and effect relationship. Mediation analysis helps us understand how or why one variable affects another by examining a mediator, which is a variable that transmits the effects. For example, stress might mediate the relationship between workload and employee productivity. This means that a heavy workload increases stress, and stress in turn reduces productivity. By studying a mediator, we can see a step by step process of how changes happen. This type of analysis is useful because it reveals the underlying mechanisms of cause and effect. If we know that stress is the reason workload affects productivity, we can address stress directly, perhaps through better time management or support systems, to improve productivity without necessarily reducing the workload. The counterfactuals allow us to ask what if question by comparing what actually happened to what could have happened under different conditions. For example, to estimate the effect of a scholarship program, we compare the outcomes of students who received the scholarships to those who didn't but were otherwise similar. This helps us understand the true impact of the scholarship. Counterfactuals are powerful because they help us evaluate interventions that can't be tested in real life experiments. For instance, we can't go back in time and give a scholarship to someone who didn't receive one. But by using the data and statistical methods, we can estimate that what might have happened. This approach is widely used in policy evaluation, medicine, and business to make informed decisions. The potential outcomes framework is a way to define causal effects by comparing outcomes under different conditions. For example, to study the effect of college and earning, we compare the actual earnings of college graduates to what they might have earned if they hadn't attended college. This requires us to account for other factors like family background or work experience to make a fair comparison. This framework is essential because it helps us understand the true effect of a treatment or intervention. Without it, we might confuse correlation with causation. For instance, assuming college causes higher earnings when in reality the factors like motivation or family wealth could be responsible. By carefully comparing potential outcomes, we can draw more accurate conclusions. A randomized controlled trial, or RCT, is an experiment where participants are randomly assigned to either a treatment group or a control group. For example, to test a new vaccine, some participants receive the vaccine while others receive a placebo. Randomization ensures that groups are similar in all other aspects, so any differences in outcomes can be attributed to the treatment. RCT, or randomized controlled trials, are considered the gold standard for establishing causality because they minimize bias. If the vaccine group shows significantly better health outcomes than the placebo group, we can be confident that vaccine works. RCTs are commonly used in medicine, psychology, and economics to test the effectiveness of interventions. In observational studies, researchers don't intervene, they simply observe and analyze existing data. For example, studying the effects of air pollution on respiratory health using historical records. Unlike RCT's, observational studies can't randomly assign treatments, so researchers rely on methods like DAGs to infer causality, while observational studies are less controlled than RCTs. They are often more practical, especially when experiments are unethical or impossible. For instance, we can't randomly expose people to air pollution, but we can analyze data from different cities with varying pollution levels to understand its effects. These studies are valuable but require careful analysis to avoid misleading conclusions. An instrumental variable, or IV, is a tool used to study causal relationships when randomization is not possible. The IV affects the treatment but not the outcome, except through the treatment. For example, distance to college can be used as an instrument to study the effects of education on earnings. People who live closer to colleges are more likely to attend, but distance itself does not directly affect earnings. IVs, or instrumental variables, help us isolate the effects of treatment by acting as natural experiment. If we find that people who live closer to colleges earn more because they are more likely to attend, we can infer that education causes higher earnings. IVs are especially useful in economics and social sciences, where controlled experiments are often impractical, not practical. Epidemiology uses causal inference to identify the causes of diseases and evaluate public health interventions. For example, determining whether a new public health campaign actually reduces smoking rates by comparing smoking rates before and after the campaign, or between areas with and without the campaign. Researchers can assess its effectiveness. This field is critical for improving public health. If we can prove that a campaign causes to drop in smoking, governments can invest in similar programs. Causal inference helps separate real effects from coincidences, ensuring that health policies are based on solid evidence. Economists use causal inferences to evaluate the impacts of policies or economic interventions. For example, assessing how a minimum wage increases affects employment rates by comparing employment levels before and after the wage hike, or between regions that different wage laws. Economists can determine whether the policy had the intended effect. Causal inference in economics helps policymakers make data-driven decisions. If a minimum wage increases leads to job losses in some industrial but not others, this information can guide future policy adjustments without causal analysis. It is easy to misinterpret correlations as causation, leading to ineffective or harmful policies. Public policy relies on causal inference to understand the effects of specific actions, such as new transportation policy on traffic congestion, by comparing traffic patterns before and after the policy, or between cities and without the policy. Policymakers can determine whether the change was effective. This approach ensures that policies are evidence-based. For instance, if a new bus route reduces congestion, the policy can be expanded. If not, resources can be redirected to more effective solutions. Causal inference helps governments spend taxpayer money wisely and achieve outcomes for communities. Causal inference faces challenges like unmeasured confounding, hidden factors that bias results, model misspecification, incorrect assumptions in analysis, and data limitations, incomplete or poor quality data. These issues can lead to incorrect conclusions if not addressed carefully. The future of causal inference is exciting, with advances in AI and machine learning enabling more personalized and precise analysis. For example, AI can help tailor medical treatments to individual patients based on their unique data, improving outcomes. As technology evolves, causal inference will become even more powerful, helping us solve complex problems in healthcare, economics, and beyond. Hopefully, this has given you some thought process to think about. Let's continue in the next lecture. Take care.